Hey folks, how's it going? In this video we're going to go over conservation of energy. So let's get started. Now conservation of energy is all to do with one type of energy changing into another form of energy. It says here that the law of conservation of energy, which is also known as the principle of conservation of energy, states that energy cannot be created or destroyed, but it can change from one form to another. Another way of saying this though is that during any energy transformation, the total amount of energy is always conserved. So this means we cannot create energy from nothing, and we also cannot just completely get rid of energy, but we can change its form. So for example, imagine dropping a ball from rest at a height above the ground. The gravitational potential energy of the ball turns into kinetic energy since the ball is now moving. So here's a picture of a person holding the ball above the ground, and right now the ball has this stored gravitational potential energy being raised above the ground, and when they let the ball go, that gravitational potential energy is converted into kinetic energy. It then says that this problem would require setting the gravitational potential energy equal to the kinetic energy. So you could say here that by conservation of energy, assuming no energy losses, the EP is equal to EK, or you could rewrite this in terms of the equations. So we have mgh for the gravitational potential energy is equal to a half mv squared for the kinetic energy. And this would allow you to calculate things like the height of the ball to begin with, or the speed of the ball just before it hits the ground, for example. So here we have another example of conservation of energy, where we've got a skater who, if we put up to the top of the ramp here, is going to have a gravitational potential energy to begin with, but if I let her go, then that gravitational potential energy is going to change into kinetic energy as she's moving, as shown here. Now, an important point to make is that during calculations using conservation of energy, we often assume no energy loss is due to friction or air resistance and things like that. But in reality, this wouldn't be the case. So in this example, if I was to let the skater go here with no friction on the track, then they should just keep going to the same height each time. And we know that this wouldn't really be the case in real life. However, if I was to increase the friction between the skateboard and the track, then we should start to see that the skater doesn't go to the same height each time, and that there are energy losses. So this would be more realistic. Going back to the notes, another example of energy conservation includes a pendulum in which the gravitational potential energy turns into kinetic energy and then back into gravitational potential energy again during a swing from one side to the other. So let's say the ball on the end of this string started off at the highest point of its swing. We would say that at this point it's got maximum gravitational potential energy because it's the highest point above the ground. And then when we let that go, the ball is going to move, so it's going to gain kinetic energy as it moves through the middle point, i.e. the equilibrium of its swing. And at this point, we could say that the ball is going to have its maximum speed and therefore maximum kinetic energy. Because remember, kinetic energy depends on both mass and speed. And the mass is staying the same here. And because we're at the lowest point of the swing here, the lowest height, that means we have minimum gravitational potential energy. As the ball continues to move up to the other extremity of the swing, up to this point, again we can say it's got no kinetic energy once it comes to a stop, but it does have maximum gravitational potential energy again. So as the ball swings through this motion, it's going to just go back and forth between these types of energies. Now, I'll just show you a quick simulation of this pendulum to help you understand it. So here we have a mass on a string suspended from this point up here, and I want you to pay attention to this energy graph on the left hand side, and we can ignore any thermal energies shown in red. So if I take the mass on the end of the string and I raise it to a certain angle, let's say 45 degrees, then you'll notice I have maximum potential energy on the left hand side on my energy graph, and that's because we're at the highest point of the swing. As I then let this pendulum go, we're going to see a change from gravitational potential energy into kinetic energy and then back to gravitational potential energy again. So just to show you that here, you can see that the energy is constantly changing between the kinetic energy and the gravitational potential energy. Now, if we were to slow down that swing, you'll be able to see that at this point, we've got maximum potential energy. At the equilibrium position in the middle, we've got maximum kinetic energy. And then at the other extremity, we've got maximum potential energy again. Now remember, in everyday life, this is not going to be the case because this assumes no energy losses due to air resistance or friction. But if we were to increase the friction here, for example, we would see that the mass doesn't go up to 45 degrees each time. The swings should get smaller and smaller in size. So if we increase the friction here, you'll see that the string and the mass doesn't move to the same point each time. It's actually losing energy over time. Lastly, going back to the notes, another situation involving conservation of energy might involve doing work to lift an object from the ground to a certain height. This means that the work done turns into gravitational potential energy. So if there's a situation where an object is being lifted up and work is being done to do that, to raise it to a certain height above the ground, we can say that work done is converted into gravitational potential energy. So you can see that from the diagram here. The box initially has no gravitational potential energy, but the guy is doing work to raise it above the ground. And this situation would require setting the work done equal to the gravitational potential energy. So we could say that EW is equal to EP, again assuming no energy losses. And this means we could rewrite this in terms of their equations. FD for work done is equal to mgh for the gravitational potential energy. So you would be able to find things here like the mass of the object, the height, the distance moved, or the force applied to the object, for example. Now, one last thing to mention is that when you're doing problems involving conservation of energy, it's up to you whether you want to equate two energies together like this and then put numbers in and then simplify, or whether you want to split it up into parts. Now, some of you might find that easier to do one energy calculation first and then put the answer that you get for that energy into the other equation for energy, making the energies equal. But it's really just preference, so you go with whatever one you're comfortable with. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.